In this lesson, we'll be talking about accumulation functions and one part of the Fundamental Theorem of Calculus. So we have previously established that a definite integral, so the integral from a to b of f of x dx, represents the area bounded by a curve and the x-axis on the interval a to b. What if we know where the interval starts at a, but we don't know where it ends? So we're going to use x to represent that value. Let capital F of x be a new function that represents this scenario. So capital F of x equals the definite integral from a to x of f of t dt. For a given value of x, we can determine the area between f of t and the x-axis. And you're going to see in this video us apply that idea for a bunch of values in just a few minutes. This also relates to one part of the Fundamental Theorem of Calculus. So this part deals with taking the derivative of an antiderivative. And if we think about those terms, they sound like opposites of one another, right? Derivative and antiderivative. So the Fundamental Theorem of Calculus says that if a is a constant and f of t is a continuous function on the closed interval a to b, that when we take the derivative, okay, so here's our derivative of the integral from a to x of f of t dt, that is equal to f of x times 1. And that equals f of x, of course, because timesing by 1 is not going to change the value there. But why are we multiplying by 1? That's basically because of chain rule, that is the derivative of the upper bound. So if, for instance, the upper bound was 2x, we would multiply by 2. Another way this could be expressed is if g of x is equal to the integral from a to x of f of t dt, then g prime of x is equal to f of x. So for example, if g of x is equal to the definite integral from 2 to x of t squared dt, then g prime of x is equal to x squared. All right, let's take a look at an actual question here, because I know that sometimes all that information can be a lot of technical calculus jargon, but let's try and make sense of it. And if we think back to something you've learned in Algebra 1, you learned how to make a table of values for a function. You plugged in the x value into the function so that you were able to determine the y value, the output. We're going to basically be doing the same thing here, but incorporating definite integrals. So it says, let f of t be the graph shown below, where capital F of x is equal to the definite integral from 0 to x of f of t dt, and we're going to fill out this table of values. So if I take a look at this here and just zoom in, we are going to be plugging in each value of x from the table of values in for that upper bound. So if I take a look at when x is 0, I'm basically finding the definite integral from 0 to 0 of f of t dt. And let's recall what a definite integral represents. It represents area under a curve. So we're looking for the change in area from 0 to 0. Nothing is changing in there. So whenever the bounds are equal, the definite integral is always equal to 0. Let's take a look at one that would be different though. So if I change that upper bound to a 1, and I take a look at our graph here, we know that definite integral is the area under the curve, so I'm looking for the area under the curve, or in this case, the line, from 0 to 1. And I can see that that's rectangular, and it would have an area of 6. So that means capital F of 1 is equal to 6. All right, let's do it for when x is 2. Go to our graph. If I look at 0 to 2 here, from 0 to 1, it was 6. From 1 to 2, it's 6 again. It happens to be. And so that means that our output is going to be 12. We are accumulating the new areas each time. We're adding the new area to the previous area. All right, from 0 to 3 means now I'm going to have to take that 12 and add on the new area from 2 to 3. If I look from 2 to 3, I actually have a trapezoid this time. So area of a trapezoid is 1/2 the height, which is 1 in this case, base 1 plus base 2, and that area is going to be 3.5. So I'm taking 12, adding 3.5 to it, and that gives me 15.5. All right, now let's repeat this process, and feel free, I'm going to fill this in here. Feel free to pause the video if you need more time to fill in your areas. I'm just going to set these up first. All right, from 0 to 4, we're taking that previous area of 15.5, and you can see we're adding 1 to it, so that's going to give me 16.5. From 4 to 5, we're adding in 1.5. That's another trapezoid, so that's going to give me 18 as the output. And then from 5 to 6, we are adding in 2.5, again, another trapezoid, and that will make capital F of 6 equal to 20.5. So now we have successfully filled in our table of values from 0 to 6. Let's take a look at another example. The graph of a function f is shown below, which consists of linear pieces and a semicircle. Let g of x equal the definite integral from 0 to x of f of t dt. We're going to first find g of 2. Well, that's basically the same thing we did on question 1. We're going to plug 2 in for the upper bound, and we're going to calculate the area from 0 to 2. If I take a look at our graph here, we see that we have a trapezoid, and here are our bases. In the previous example, the bases were going vertically. Now they're horizontal. So this is going to be 1/2. Height is 2. Base 1 plus base 2. So 2 plus 1. And g of 2 is equal to 3. Now g prime of 2, that's where we get into the fundamental theorem of calculus. So we know that g of x is equal to the definite integral from 0 to x of f of t dt. But if I take the derivative of that, according to the fundamental theorem of calculus, that's going to be equal to f of x, or f of x times 1. And now we're going to plug 2 in, since this problem is asking for g prime of 2. That means we're really looking for f of 2, and if you look at our graph to the right, f of 2 is just 0. All right, let's try that process once more, but with a new input. So g of 6 means I'm going to be finding the area from 0 to 6. Now, we already know that the area from 0 to 2 was 3. So we have to add in the area from 2 to 6 now, right? So if we look at our graph here, this all came out to be 3. We've got to add in all of this new area. Well, that is a semicircle, and area of a circle is pi r squared. So this is going to be 1/2 pi r squared, and I can see that the radius is 2. That's going to come out to be 2 pi. So my answer here is going to end up being 3 plus 2 pi. And finally, part D is similar to part B. Since we know that g prime of x is equal to f of x, g prime of 6 is just equal to whatever f of 6 is, and that happens to be 0 again on our graph.